We're diving into the foundations of modern software engineering today. Specifically, we're undertaking a targeted review of functional programming. We'll be extracting the crucial principles and techniques laid out in the source material, The Art of Functional Programming. It's worth noting for transparency that our analysis outline was generated with the assistance of an AI system, based exclusively on the source text. So if you're looking to transition your thinking from that mutable, stepwise logic of classic programming to a more expressive and compositional style, this should be a helpful map. We'll be synthesizing concepts across various languages, OCaml, Haskell, and even looking at Java streams to provide a comprehensive thematic understanding of why this paradigm is, well, rapidly becoming so essential. Okay, let's start at the very beginning with the paradigm shift itself. The source material presents functional programming, or FP, as not just a set of rules, but as an elegant, powerful philosophy. It really emphasizes abstraction and composition. These are, the two pillars that lead to highly concise, safer, and ultimately more scalable solutions. The goal isn't just to learn the syntax of, say, Haskell. It's to truly master the underlying principles that apply universally, whether you're using Swift, Kotlin, Python, or even the JavaStream MPI.
What's fascinating here is the intentional step backward the text takes to provide some historical context. To truly understand the functional style, you really have to understand the constraints that the imperative style was born under. The imperative paradigm, which most of us probably learned first in languages like C or Java, is very tightly coupled to the von Neumann architecture. If you think of a computer modeled that way, it's essentially a giant block of memory cells in a sequential processing unit. So programming in that model becomes a sequence of explicit commands that change the memory state. The focus is literally, first do this, then do that.
So we're constantly managing this idea of a mutable state, because the hardware itself sort of demands that we treat programming like a series of chores to be done in a specific order.
Precisely. Functional programming breaks that architectural dependency. It offers a descriptive alternative. Instead of telling the computer how to calculate something, setting up a loop counter, initializing a sum, mutating that sum, you just describe what you want. Take the classic example, calculating the sum of squares of the first n numbers. An imperative solution is, well, quite verbose and low level. A functional solution, maybe expressed as something like fold plus 0 map square 1n, is descriptive. It's built from reusable general-purpose components.
So you have map to transform the list, fold to aggregate the result.
Exactly, and function composition to string them together. The cognitive load shifts entirely from micromanaging memory to understanding these higher-level concepts.
And this is where that idea of composition really shines, isn't it? If you suddenly needed to calculate the sum of squares of only the prime numbers in that sequence, the imperative approach would force you to disrupt the whole loop structure, maybe inserting a conditional if statement. It's a low-level, high-risk change.
But in the functional world, you simply plug in another generalized tested component, filter as prime, right into the existing chain. It just snaps into place without altering the underlying logic of squaring or summing. And this is the core advantage: higher abstraction and superior composability. This mindset is critical because if we look at the bigger picture, the entire industry, from declarative UI frameworks to build tools like Gradle and even infrastructure as code, is moving toward this declarative way of thinking.
So if that's the paradigm shift, what's the fundamental building block? If we're moving away from state management, the source makes it clear that everything in FP revolves around the expression.
It does, and this is a fundamental, almost philosophical departure from imperative languages. Imperative languages, they operate in two distinct worlds: the world of expressions, which evaluate to values like 1 plus 1, and the world of statements.
Statements being the commands that perform side effects, like variable assignments or loops.
Exactly. In the functional paradigm, we entirely unlearn the concept of a statement. Every piece of logic, including conditional branching, is handled through an expression. And when we look at any expression, we have to analyze its three technical aspects: syntax, types, and semantics.
That's a great breakdown. So syntax just handles the valid structure, making sure your OCaml code is legal and not, say, just random characters.
Correct. But types are the security layer. Static typing, which you see in powerful FP languages like Haskell and OCaml, means a type checker is constantly preventing basic errors that might only show up in production with dynamically typed languages.
It actively prevents those strange scenarios, like in JavaScript, where 1 plus true might evaluate a 2 through some silent error-prone conversion.
Precisely. And finally, semantics gives meaning to that structure. It defines how a syntactically and type-correct expression maps to a final value. This can happen through interpretation, which is direct evaluation, or compilation, where the code is transformed into an abstract syntax tree and then compiled to bytecode or native code.
And before we move on, there's a crucial detail about naming. If names aren't labels for mutable memory cells, what are they in FP?
Names are assigned to expressions solely for abstraction, to, chunk information and provide clear labels for a computation. They are fundamentally immutable bindings to specific values. This is completely distinct from the imperative view, where a variable is a volatile memory location whose content is expected to change.
Okay, so if the expression is the foundation, then the structure we build with it must be functions. Chapter 3 introduces the mathematical basis for all of this. The lambda calculus. The power here is recognizing functions as first-class citizens. They're basically data, meaning they can be passed as arguments, returned as results, and bound to names just like any other value.
And from the lambda calculus comes a very profound technical insight called currying. Instead of having a single function that takes, say, 3 arguments at once, currying represents that function as a chain of nested single-argument functions.
And this is what enables partial application, right?
That's the key. If you have a function like tax rate, base price quantity, you can lock in the rate argument. What you get back is a brand new specialized function, maybe California tax, that now only needs the other 2 arguments.
That seems like it would dramatically reduce boilerplate code. But let's talk about performance. When we define functions, how does the system actually treat the arguments that we pass in?
That brings us to evaluation strategies. OCaml and most mainstream languages use what's called call by value, or strict semantics. The arguments are evaluated immediately before the function body even runs. So if you pass an expression that causes an error, like division by 0, the program crashes, even if that argument isn't ultimately used.
And the alternative?
Contrast that with Haskell's approach, call by name, which is non-strict or lazy. Here, evaluation is deferred. The argument is only calculated if and when the function body actually needs the value.
Now, since we're in a paradigm without traditional for or while loops, iteration has to shift completely to recursive functions. But that raises a big question. If we use recursion to iterate over huge data sets, are we just going to blow the stack and cause a catastrophic memory failure? That's the common worry.
That is the essential worry. And it highlights the danger of what we call non-tail recursive functions. Your intuition is correct. A simple recursive sum function will create linear growth in the call stack. You'll see frame after frame waiting for the result of the previous call, leading directly to a Stack Overflow error.
So what's the functional solution to that problem?
It's the tail recursive function. This is defined by one single critical property. The final recursive call must be the absolute last action the function performs. If that property is met, a compiler like OCaml's can perform tail recursion optimization. It compiles the function into bytecode that completely avoids building up a call stack.
So it effectively turns the recursion into a highly efficient jump operation.
Exactly. It becomes the declarative, safe equivalent of a loop. This is arguably one of the most important concepts for writing scalable functional code.
That is a phenomenal technique. And zooming out from optimizing single functions, we get to the concept of higher order functions, or HOFs. This is where true abstraction really happens.
Indeed. HOFs are functions that either accept or return other functions. They are the mechanism for defining highly general computation methods. Using HOFs allows the programmer to climb the abstraction hierarchy. You capture generic patterns that apply across dozens of specific problems. This massively reduces code duplication.
Now that we have the logic down, let's talk about data. Chapter 4 pivots to compound data types, starting with simple structures like tuples for grouping-related data. But the real power seems to lie in how we unpack that data, using pattern matching.
Pattern matching is the clean, powerful mechanism that FP uses instead of, cumbersome accessors or explicit type checks. Using the match keyword, you can safely decompose complex data structures, ensuring all possible forms of the data are handled. This improves both code safety and clarity.
And this idea extends to recursive structures like lists, where the empty list is the natural base case for any function. But what about when we need to define our own custom data structures?
That's where algebraic data types, or ADTs, come in. ADTs allow you to declare your own custom types that are hierarchical and highly constrained. Even built-in types like bool or list and OCam are actually defined internally as ADTs. This framework forces a very direct and illuminating comparison to object-oriented classes, which leads us right into the famous expression problem.
They seem similar on the surface, but their strengths are inverted, is that right?
Perfectly inverted. Classes, especially with inheritance, make adding new data representations easy. You just create a new subclass. But adding new operations is difficult because you might have to modify every existing class.
And ADTs are the opposite.
Exactly. With ADTs and pattern matching, adding new operations is easy. You just add a new case to your match expression in one place. But adding a new representation means you have to go update every function that matches on that ADT. The practical rule of thumb is clear. If you expect your data types to evolve constantly, use classes. If you expect your operations to evolve constantly, use ADTs.
This systematic approach to data leads us right into Chapter 5, focusing on the most general and reusable HOFs that capture universal computation patterns. If you're going to master FP, you have to master map, filter, and fold.
Let's start with map. Map is the abstraction that says, I have a function, f, and I want to apply it uniformly to every element of this structure, a list, a tree, whatever, and give me a new structure back.
It treats the entire data transformation as a single conceptual unit.
And its generality is immense. It moves beyond just lists to hierarchical trees and even into utility structures for things like error handling. The option.map example in the book is perfect. It lets you chain operations on an optional value, and if that value is missing, the entire chain safely collapses without an error.
Then we have filter, which is the abstraction for selection. It reduces a collection based on some condition or a predicate.
But the true workhorse of the group is fold, which is sometimes called reduce. Fold is the most generalized abstraction there is for aggregation. It takes a binary function and an initial value, and it iteratively combines all the elements of a structure. Functions like sumList or prodlist are just specific instances of this single, powerful HOF.
The book emphasizes its generality by showing it can fold over not just lists, but also recursive binary trees.
It even folds over the unary representation of natural numbers. The key takeaway is when you define a new recursive data structure, the most valuable next step is often to define its corresponding fold function.
Building on these HOFs, Chapter 6 introduces data flow programming. This paradigm moves away from sequential control flow and focuses entirely on the movement of data between components.
This approach offers some significant benefits. The resulting programs are easier to understand because they're built from small, isolated components, and critically, it enables automatic parallel execution. A data flow executor can easily determine the dependencies between components, and if they don't depend on each other, they can run at the same time.
The evolution of this concept then leads to stream-based data flow programming. What was the need for streams? Why not just stick with lists?
Streams are required when you need to compose programs that have to handle signals containing an infinite number of elements. And you need to do this while maintaining the efficiency of incremental computation.
Because you obviously can't compute an infinite list up front.
Exactly. Streams solve this using lazy evaluation, which is triggered on demand. If you need the 10th element of an infinite stream of prime numbers, only the first 10 are ever computed, and only when you request them.
Finally, let's ground all this in the real world in Chapter 7. There's this lingering myth that FP is only for, math stuff.
And the source expertly argues that FP is highly relevant for enterprise applications involving data processing, whether that's in e-commerce, web backends, or mobile services.
Data handling seems to be the perfect use case. Managing collections becomes almost trivial in a declarative way with functions like list.sort or takewhile.
But the clearest application is handling JSON data, which is the lingua franca of the modern web. JSON's hierarchical structure is an excellent fit for functional techniques. You can cleanly represent complex JSON structures using algebraic data types, defining specific types for object, array, int, string, and so on.
Which gives you complete type safety and clarity right from the start.
It does. And manipulation then becomes very elegant, using pattern matching and HOFs. For instance, using a specialized member function for robust data extraction, or a JSON array map to transform an array of complex actor records. It shows how high-level composition maximizes reusability in complex data transformation pipelines.
We have completed our systematic extraction of the core technical material from the source text. If there is one overarching message for you to take away, it is that functional programming's immense power comes from its commitment to two ideas. First, superior abstraction, realized through first-class functions and HOFs like map, filter, and fold. And second, unparalleled composition, which allows you to build complex systems by snapping together small, reusable, and tested components. We would strongly recommend you dedicate time to reading the full book, The Art of Functional Programming, to deepen your knowledge. The author also suggests several foundational resources to truly complete your understanding of this shift, specifically structure and interpretation of computer programs, or SICP, and thinking functionally with Haskell. Ultimately, the declarative way of thinking taught by functional programming is a skill that transcends any single language. The fundamental principles we discussed today, immutability, expression-based logic, and compositional functions, remain valid and, well, immensely valuable regardless of what language you're writing in tomorrow. We encourage the friends of the show to subscribe for more expert analysis of source material, and we wish you a great day.